In 1891, Chicago's Monadnock building reached just 16 stories, and its brick walls had to be 6 feet thick at the base to support their own weight. That was the absolute ceiling of vertical construction. Today, towers rise past 800 meters. From the first steel frames of 1885 to the megatalls now planned for 2040, every generation of builders has confronted limits believed to be final, and the next one may actually be. For centuries, gravity dictated that the taller a building grew, the thicker its lower walls had to be to prevent the structure from collapsing under its own weight. This structural penalty swallowed valuable ground floor real estate, making extreme height economically impossible. The breakthrough came when architects split the two primary functions of a wall, keeping the weather out and holding the building up. In 1854, Elisha Otis demonstrated his safety brake at New York's Crystal Palace, proving that an elevator platform would not freefall even if its hoisting rope was severed. This mechanical failsafe instantly turned the undesirable upper floors of a building into premium, rentable space. 3 decades later, at the corner of LaSalle and Adams Streets, William LeBaron Jenney applied an unprecedented structural concept to the home insurance building. Completed in 1885 at 10 stories and 138 feet, and later expanded to 12 stories, Jenney's design utilized a hybrid skeleton of cast and wrought iron. By transferring the floor loads to an internal metal cage, the exterior walls no longer had to carry the weight of the building. They merely hung from the frame like curtains. Protected by clay tile fireproofing and anchored into Chicago's soft soil by concrete caisson foundations, this skeleton frame dissolved the physical limits of masonry and established the structural blueprint of the modern skyscraper. At the turn of the 20th century, vertical architecture shifted from structural experimentation to an aggressive pursuit of prestige. In 1902, Daniel Burnham designed the Flatiron Building, using a rigid steel bracing system to raise 22 stories and 285 feet over a triangular Manhattan lot. Within 6 years, the height benchmark moved rapidly. Architect Ernest Flagg and engineer Otto Semch pushed the ceiling to 612 feet with the 47-story Singer Building, anchoring its slender frame with deep pneumatic caissons. In 1909, Pierre Lebrun completed the Metropolitan Life Tower, clad in Tuckahoe marble, reaching 50 stories and 700 feet. Cass Gilbert's Woolworth Building surpassed it in 1913, rising 57 stories to 792 feet beneath an ornate Gothic terracotta skin. By the late 1920s, corporate competition turned construction into a fast-paced media event. Architect William Van Allen won the crown for the Chrysler Building in 1930 by secretly assembling a 186-foot stainless steel spire inside the frame and hoisting it through the roof in 90 minutes, reaching 1,046 feet. This victory was short-lived. In 1931, Shreve, Lamb, and Harmon completed the Empire State Building, rising 102 stories and 1,250 feet to the roof. Built in just 1 year and 45 days, the project employed 5,000 workers, utilizing standardized steel and synchronized logistics to erect up to 4 floors a week, proving that industrial coordination had become the defining instrument of height. By the early 1950s, a new architectural philosophy stripped skyscrapers of masonry ornament, replacing stone with glass and metal skins. The 21-story Liver House and the 38-story Seagram Building, designed under the influence of Ludwig Mies van der Rohe, established the glass curtain wall as the new corporate standard. These non-load-bearing exterior walls hung from internal steel frames, opening interiors to natural light, but leaving the fundamental structural system unchanged. As buildings pushed taller, traditional steel frames became prohibitively expensive due to the massive amount of steel required to resist wind sway. In the 1960s, structural engineer Fazlur Rahman Khan of Skidmore, Owings and Merrill introduced a structural shift, the tube system. Instead of relying on a dense grid of interior columns, Khan moved the structural load-bearing and wind-resisting elements to the perimeter of the building, creating a rigid hollow cylinder. This approach debuted on a grand scale with the John Hancock Center in 1969. Rising 100 stories and 1,128 feet, the tower used exterior diagonal steel members to form an X-braced tube, reducing steel requirements by 30% compared to conventional frames. Khan then scaled this logic at the Sears Tower in 1974. By bundling 9 square tube modules together, the 110-story, 1,450-foot structure achieved unprecedented height with minimal material. Moving structural resistance to the exterior expanded usable floor area, proving that structural performance had replaced applied ornament as the primary measure of progress. In 1998, architect Cesar Pelli completed the Petronas Twin Towers in Kuala Lumpur. Rising 88 floors and 452 meters, or 1,483 feet, the towers bypassed traditional structural steel in favor of a high-strength silica fume concrete core and an outer ring of 16 massive columns, establishing the super-tall skyscraper as a vehicle for national prominence on the global stage. In 2004, Taipei 101 raised the height ceiling to 508 meters, or 1,667 feet. To protect the 101-story tower from frequent typhoons and earthquakes, engineers suspended a 660-ton steel-tuned mass damper between the 87th and 92nd floors. This massive, visible sphere counteracts lateral wind forces by swaying in direct opposition to the building's movement, making dynamic motion control a standard element of high-rise engineering. The ultimate transition to extreme height structural optimization arrived with the Burj Khalifa in Dubai, constructed between 2004 and 2010. Designed by architect Adrian Smith and engineer Bill Baker, the structure climbs 163 floors to 828 meters, or 2,717 feet. To achieve this height, Baker engineered the buttressed core, a Y-shaped concrete hub where 3 wings support a central hexagonal tower to prevent twisting and resist wind loads. Aerodynamic tapering, intensive wind tunnel testing, and specialized high-strength concrete pumped to record heights replaced traditional steel frames, proving that extreme altitude requires highly customized structural physics. In Saudi Arabia, the Jeddah Tower was designed to reach approximately 1,000 meters, or 3,280 feet. Ground broke on the project in 2013, utilizing a 3-winged buttressed core design and a deep-piled raft foundation extending more than 100 meters into the ground. Construction stalled in 2018, leaving the kilometer-high structure unfinished at 1/3 of its target height due to financial and regulatory disputes. This vertical ambition echoes earlier, unresolved conceptual history. In 1956, architect Frank Lloyd Wright proposed the Illinois, a theoretical mile-high skyscraper designed to rise 1,600 meters. Wright's tapered, cantilevered tower remained entirely on paper, restricted by mid-century wind load calculations and material limitations that rendered a mile-high structure impossible to build. Today, the future of tall buildings is constrained by carbon, livability, and systems integration. High-strength concrete and steel carry a massive environmental footprint, forcing engineers to balance height against strict sustainability metrics. Inside these massive volumes, mechanical operations present immense challenges. Moving thousands of people daily requires complex vertical transportation networks, including high-speed double-deck elevators and strategic sky lobbies. Emergency planning demands pressurized refuge floors to secure occupants during an evacuation. To manage these highly complex systems, architects no longer rely on traditional blueprints, but on digital design methods such as building information modeling, parametric design, and modular prefabrication to coordinate structural, mechanical, and architectural components before assembly begins on site. Today, engineering has shifted from overcoming gravity to capturing energy. Future megatalls are designed not just to stand, but to power our cities through kinetic wind systems and photovoltaic skins. We are no longer just building upward, we are engineering survival. Share your thoughts on the future skyline below.